Hello everyone. These are the solved problems from March 2023 question paper. The first question is using parallel axis theorem, calculate moment of inertia of a disk of mass 200 gram and radius 5 centimeter about an axis passing through its edge and perpendicular to the plane of the disk. In this problem, we have to calculate the moment of inertia of a disk about an axis passing through its edge and perpendicular to the plane of the disk. Here, to solve the problem, we have to use the parallel axis theorem, which says that I is equal to ICM plus MR square. What is ICM? ICM is the moment of inertia of the disk about an axis passing through the center of mass and perpendicular to the plane of the disk. That is, the axis is PQ. But in this problem, we have to find out the moment of inertia of the disk about an axis passing through the edge and perpendicular to the plane of the disk. That is, here the axis is AB. The axis is AB. Now using parallel axis theorem, the moment of inertia about AB is equal to the moment of inertia about PQ, that is ICM plus MR square. That is I is equal to ICM plus MR square. Now for a disk, ICM is equal to MR square by 2. Therefore, I is equal to MR square by 2 plus MR square, that is 3 by 2 MR square. This is the expression for the moment of inertia about AB. It is given that the mass of the disk M, is equal to 200 gram and that is equal to 0.2 kilogram. The radius of the disk capital R is 5 centimeter and that is equal to 0.05 meter. Substitute these values in the equation of I. We have I is equal to 3 by 2 into 0.2 into 0.05 square and this is equal to 7.5, that is I is equal to 7.5 into 10 raised to minus 4 kilogram meter square. This is the moment of inertia of the disk about an axis passing through its edge and perpendicular to the plane of the disk. The next question is calculate the Young's modulus of a wire 100 centimeter long and 3 mm thick which increases by 0.1 centimeter when stretched by a weight of 64.1 kilogram. In the present problem, we have to find out the Young's modulus of a wire. The length of the wire and the diameter of the wire is given. Here, the wire is stretched by a weight of 64.1 kilogram. The extension in the wire is 0.1 centimeter. First, let us see what is meant by Young's modulus. Young's modulus Y is the ratio of linear stress to linear strain. Y is stress divided by strain. What is stress? Stress is equal to force per area. Strain. What is strain? Strain is the change in length by original length. That is delta L divided by L. The Young's modulus Y is equal to stress divided by strain. It is given that it is given that the mass is 64.1 kilogram. To calculate stress, we have to find out the force. Force F is equal to mg, that is 64.1 into 9.8, that is equal to 628.18 Newton. This is the force. It is given that the thickness of the wire is 3 mm, that is the diameter of the wire is 3 mm. D is equal to 3 mm. This implies radius is equal to 1.5 millimeter, and that is equal to 0.0015 meter. The radius R is equal to 0.0015 meter. Now stress is equal to force per unit area, and that is equal to 628.18 divided by what is area here? Area is the area of cross section, that is pi r square. Here radius is 0.0015. Therefore stress is equal to 628.18 divided by pi into 0.0015 square, that is equal to 8.89 into 10 raised to 7 Newton per meter square. That is stress is equal to 8.89 into 10 raised to 7 Newton per meter square. Now we have to find out the strain. Because of a weight of 64.1 kilogram, the length of the wire is increased by 0.1 centimeter. That is, the change in length due to stretching is 0.1 centimeter. That is 0.001 meter. This is the extension produced in the wire. Now the original length of the wire is 100 centimeter. L is equal to 100 centimeter, and that is equal to 1 meter. Now what is strain? Strain is equal to change in length by original length, that is delta L divided by L. Here delta L is 0.001 divided by 1, that is 0.001. There is no unit for strain, that is strain is equal to 0.001. Once we have the stress and strain, we can calculate the Young's modulus as the Young's modulus Y is equal to stress by strain. Y is equal to stress divided by strain, that is equal to 8.89 into 10 raised to 7 divided by 0.001, and this is equal to 8.89 into 10 raised to 10 Newton per meter square. That is, the Young's modulus of the material of the wire is 8.89 into 10 raised to 10 Newton per meter square. The next question is, surface tension of a soap solution is 0.05 Newton per meter. How much work is done to produce the soap bubble of radius 0.03 meter? In this problem, we have to find out the work done to produce the soap bubble of radius 0.03 meter. The surface tension of the soap solution is given as 0.05 Newton per meter. That is, the surface tension S is equal to 0.05 Newton per meter and the radius of the bubble is 0.03 meter. Now, what is the surface area of the bubble? If you consider both surface of the bubble, the surface area is 2 times 4 pi r square. Also, we know that the work done in producing an area is equal to surface tension into area produced. It is given that the surface tension S is equal to 0.05 Newton per meter. The radius of the soap bubble R is equal to the radius of the bubble R is equal to 0.03 meter. When we blow the soap bubble, the area produced is 2 times 4 pi r square because the surface area of the bubble is 2 times 4 pi r square. Here we have to consider both surface of the bubble. That is, area produced is 2 into 4 pi r square, that is 2 into 4 pi into the radius is 0.03. Therefore, the area produced is 2 into 4 pi into 0.03 square meter square. Now, the work done in producing an area is nothing but surface tension into area produced. Therefore, the work done is equal to surface tension. Here, the surface tension is 0.05 Newton per meter. Therefore, the work done is 0.05 into area produced, that is 0.05 into 2 into 4 pi into 0.03 square, and that is equal to 1.13 into 10 raised to minus 3 joule. The next question is, a thin circular ring is suspended from a peg so that it can oscillate about it. Determine its period of oscillation if its radius is 10 centimeter. In the present problem, it is given that a thin circular ring is suspended from a peg. We have to find out the period of oscillation. The diagram shows a thin circular ring which is suspended. The direction of oscillation is also shown. This is the ring. This is the ring, and O is the center of suspension. This is the center of suspension, and AB is the axis that is passing through O. This ring oscillates about this point O. So this is an example of a compound pendulum with a time period T is equal to 2 pi into root of I by mgh, where I is the moment of inertia of the ring about AB and Ig is the moment of inertia of the ring about an axis PQ which is passing through the center of gravity and perpendicular to the plane of the ring. We have a standard result. The moment of inertia of the ring about an axis passing through the center and perpendicular to the plane is mr square, where m is the mass of the ring and r is the radius of the ring. In the present case, the radius of the ring is taken as h. We have the expression for the time period is T is equal to 2 pi into root of I by mgh, where I is the moment of inertia of the ring about an axis passing through the center of suspension. In the present case, it is AB, and that is equal to Ig plus mh square. Now, if h is the radius of the ring and if small m is the mass of the ring, then we can write Ig, that is the moment of inertia of the ring about an axis that is passing through the center of gravity and perpendicular to the plane is mh square. Therefore, moment of inertia about AB using parallax theorem is mh square plus mh square, that is 2mh square. Therefore, the time period T is 2 pi into root of I by mgh, that is 2 pi into root of 2mh square divided by mgh, or T is equal to 2 pi into root of 2h by g. This is the expression for the period of oscillation when a thin circular ring is suspended from a peg. T is equal to 2 pi into root of 2h by g, where h is the radius of the ring. It is given that the radius of the ring is 0.10 meter, that is, it is 10 centimeter, that is equal to 0.10 meter. Therefore, T is equal to 2 pi into root of 2 into 0.10 divided by 9.8, and that is equal to 0.898 second. This is the period of oscillation. The next question is, a solid cylinder of radius 6 cm is suspended by a vertical wire as a torsion pendulum. The axis of the cylinder is along the wire. Find the moment of torsion of the wire if the mass of the cylinder be 5 kg and the period of vibration is 4 seconds. In the present problem, a torsion pendulum is given, that is a wire which is fixed at one end, and on the opposite end a solid cylinder of radius 6 cm is suspended. This is the torsion pendulum arrangement. We have a wire which is fixed at one end, and to the opposite end a solid cylinder of radius capital R is suspended. The period of oscillation of the torsion pendulum is 2 pi into root of I by c. I is the moment of inertia of the cylinder about its axis, and that is equal to mr square by 2. In the present problem, the moment of the torsion is asked, that is nothing but the couple per unit twist. So T is equal to 2 pi into root of I by c, from which the couple per unit twist C is equal to 4 pi square I by T square. Here C is the couple per unit twist of the wire, where C is the couple per unit twist of the wire. Couple per unit twist of the wire. It is given that mass of the cylinder is 5 kg and the radius is 6 centimeter, that is 0.06 meter, and the period of oscillation, that is equal to 4 seconds, that is T is equal to 4 seconds. Since the moment of inertia of the cylinder about its axis is mr square by 2, we can write the equation of C as 4 pi square, then I is mr square by 2 divided by T square, and that is equal to 2 pi square mr square by T square. 2 pi square mr square by T square. Now let us substitute the values of m, r and t. We have C is equal to 2 pi square into 5 into 0.06 square divided by 4 square, and that is equal to 0.022 Newton meter. That is the couple per unit twist of the wire C is equal to 0.022 Newton meter. The next question is two solid cylinders of solid material having length L and 2L and radii R and 2R are joined coaxially under a couple applied between free ends. The shorter cylinder show a twist of 30 degree. Calculate the twist of the longer cylinder. In the present problem, two solid cylinders having length L and 2L are joined coaxially. We have to find out the twist of the longer cylinder. The twist of the shorter cylinder is given in the question. The experimental setup is shown in the figure. This is the shorter cylinder having length L and radius R. This is the longer cylinder having length 2L. The shorter cylinder has the radius R and the longer cylinder has the radius 2R. Here AD is the fixed end where the cylinder is fixed. So the angle of twist at this point is 0. Suppose we are applying a torque in the clockwise direction at C, then a restoring torque is produced at B and the direction is anti-clockwise. Now consider B. At B the angle of twist is theta B minus theta A. Since theta A is equal to 0, we have the angle of twist at B is theta B. Now at C, the angle of twist is theta C minus theta B. That is, if we apply torque at C, a restoring torque is produced at B. Now at equilibrium, the torque clockwise at C is equal to the torque anti-clockwise at B. That is, the twisting couple at C and the twisting couple at B are equal. What is the twisting couple? It is pi n r raised to 4 theta by 2L, where L is the length of the cylinder. Now let us find out the twisting couple at C. At C means we have a cylinder of length 2L, radius 2R with angle of twist theta C minus theta B. Therefore, the twisting couple is pi n 2R raised to 4 theta C minus theta B divided by 2 times 2L. Now let us find out the twisting couple at B. At B we have a cylinder of length L and radius R with angle of twist theta B. Therefore, the twisting couple at B is pi n r raised to 4 theta B divided by 2L. Here pi and pi cancel on both sides. N and n cancel. R raised to 4 cancel. 2L cancel. So the remaining terms are 2 raised to 4 by 2 theta C minus theta B, and that is equal to theta B. That is 8 times theta C minus theta B, that is equal to theta B. That is, on simplification we have 9 theta B, that is equal to 8 theta C, or theta C is equal to 9 by 8 theta B. Theta C is equal to 9 by 8 theta B. Now what is theta C? Theta C is the twist of the longer cylinder and theta B is the twist of the shorter cylinder. It is given that the shorter cylinder is twisted by 30 degree. That means theta B is 30 degree. Given that theta B is 30 degree, therefore theta C is equal to, or the twist of the longer cylinder, theta C, that is equal to 9 by 8 times theta b, that is 9 by 8 into 30 degree, that is equal to 33.75 degree. The next question is, a thin uniform disc of radius 25 centimeter and mass 1 kilogram has a hole of radius 5 centimeter at a distance of 10 centimeter from the center of the disc. Calculate the moment of inertia of the disc about an axis perpendicular to the plane and passing through the center of the hole. In this problem, we have to find out the moment of inertia of a disk about an axis AB, which is passing through a hole which is drilled on the larger disk. That is, we have to find out the moment of inertia of the larger disk about AB. AB is an axis that is passing through the center of the hole. This is the larger disk having radius capital R, and this is the hole which is drilled on the larger disk. The radius of the hole is smaller. This is the axis which is passing through the center of the hole. We have to find out the moment of inertia of the disk about this axis. Moment of inertia of the disk about AB is I1 minus I2. I1 is the moment of inertia of the larger disk without hole, and I2 is the moment of inertia of the disk which is removed to make a hole on the larger disk. Here sigma is the mass per unit area. First, let us find out I2. What is I2? I2 is the moment of inertia of the disk which is removed from the larger disk, so that we have a hole on the larger disk. Let small r be the radius of the smaller disk which is removed from the larger disk, and let m be the mass of the smaller disk. That is, we have removed a smaller disk of mass small m and radius small r from the larger disk. Then what is I2? I2 is the moment of inertia of the disk about an axis AB. This AB is an axis which is passing through the center of the disk and perpendicular to the plane. Therefore, I2 is mr square by 2, where r is the radius of the disk. Small r is the radius of the disk. Let the sigma be the mass per unit area. If sigma is the mass per unit area, then mass is equal to sigma into area. Here the area of the smaller disk is pi r square. Therefore, mass is sigma pi r square. Hence, I2 is equal to sigma pi r square, then r square divided by 2. That is sigma pi r raised to 4 divided by 2. That is the moment of inertia of the disk which is removed from the larger disk is sigma pi r raised to 4 divided by 2. Now let us find out the moment of inertia of the larger disk without hole. Here the axis is AB. This axis AB is at a distance A from the center. Therefore, moment of inertia of the disk about AB can be determined using the parallel axis theorem. If I1 is the moment of inertia of the disk about AB, then this I1 is ICM plus MA square. What is ICM? ICM is the moment of inertia of the disk about an axis PQ, where PQ is an axis that is passing through the center of mass and perpendicular to the plane of the disk. And here capital M is the mass of the larger disk, and small a is the distance between the hole and the center of the larger disk. That is, moment of inertia of the larger disk about AB is ICM plus MA square. ICM is the moment of inertia of the disk about PQ. Let capital R be the radius of the larger disk. Radius of the larger disk. First, let us find out ICM. ICM is mr square by 2 because it is a moment of inertia of the disk about an axis PQ which is passing through the center of mass. Therefore, I1 is equal to mr square by 2 plus ma square. Again, here sigma is the mass per unit area. Therefore, mass is equal to sigma into area. Here, area of the larger disk is pi capital R square. Hence, I1 is sigma pi R square, R square by 2 plus sigma pi R square, A square. That is, moment of inertia of the larger disk without a hole, I1 is sigma pi r raised to 4 by 2 plus sigma pi r square a square. That is, I1 is equal to sigma pi r raised to 4 divided by 2 plus sigma pi r square a square. Now we have I1 and I2 so that we can find out the moment of inertia of the disk about AB as I1 minus I2. That is, I is equal to I1 minus I2. We have I1 and I2. I1 is sigma pi capital R raised to 4 by 2 plus sigma pi capital R square A square, then minus I2, that is minus sigma pi small r raised to 4 divided by 2. And this is equal to sigma pi divided by 2 into, within bracket, capital R raised to 4 minus small r raised to 4 plus 2 times r square a square. This is the moment of inertia of the disk about AB. Now let us find out the mass per unit area. If capital M be the mass of the disk, then the mass per unit area is M divided by pi into r square minus small r square. That is, the mass per unit area is capital M divided by pi into capital R square minus small r square, where capital M is the mass of the larger disk. Therefore, I is equal to M divided by pi into capital R square minus small r square into pi by 2, then capital R raised to 4 minus small r raised to 4 plus 2r square a square. Here pi and pi cancel. Therefore, the moment of inertia of the disk about AB is m by 2 times capital R square minus small r square, then r raised to 4, r raised to capital R raised to 4 minus small r raised to 4 plus 2 times capital R square small a square. This is the expression for the moment of inertia of the disk about AB. Now let us substitute the given values so that we can find out I. Given capital R is 25 centimeter, that is 0.25 meter. And capital M is the mass of the larger disk, which is 1 kilogram. Then small r, that is equal to 5 centimeters, that is equal to 0.05 meter. A is the distance between the hole and the center of the larger disk, that is 10 centimeter. This is equal to 0.10 meter. Hence, the moment of inertia of the disk about AB is 1 divided by 2 times 0.25 square minus 0.05 square, 0.05 square, then within bracket 0.25 raised to 4, 0.25 raised to 4 minus 0.05 raised to 4 plus 2 times 0.25 square into 0.10 square. 0.10 square. And that is equal to 1 divided by 0.12 into 0.0039 plus 0.00125, and this is equal to 1 by 0.12 into 0.00515, and this is equal to 0.0429 kilogram meter square. That is, the moment of inertia of the disk about AB is 0.0429 kilogram meter square.